Hello students, let's continue with our optical isolation method. Then next topic is racemization. Now racemization is actually exactly opposite to that of the resolution. Resolution is the process of separation of the racemic mixture into two dextro or LIGO form. Now racemization is the process of converting an optically active compound, whether it is a dextrorotatory or a levorotatory, into its racemic mixture using a suitable experimental conditions like heat, light or certain chemical reagents. So this process is called as racemization. Now this process involves change of half of the active compound to the isomer of the opposite rotation, and that's how the racemic mixture is formed. For example, if we take any compound which is dextrorotatory, if we take 2 moles of A and if we carry out the reaction under the influence of suitable experimental conditions, then at the end of the reaction we can see that out of the 2 moles, 1 mole of the sample is converted, 1 mole of the dextroisomer is converted into the levoisomer, and 1 mole is as such in the dextro form. So that means we have got a mixture of dextro and levoisomer of the substance. The optically active hydroxy acids like lactic acid or malic acid or tartaric acid, which contain hydrogen on the carbon, that is alpha position to the carbonyl carbon, generally undergo racemization in presence of base, which means that every optical isomer cannot undergo racemization. Only those compounds, or particularly the hydroxy acids which contain the hydrogen on the carbon, which is at the alpha position of the carbonyl carbon. So they have carboxyl group that is adjacent to the asymmetric carbon, and the optically active substances which do not have a hydrogen atom at this carbon, they cannot undergo. That means all such compounds which contain a hydrogen at the alpha position to the carbonyl carbon can undergo racemization. All other optically active isomers which do not contain such type of position of hydrogen cannot undergo racemization. Here we can see, for example, racemization of lactic acid. Now here, racemization of one enantiomer by heating takes place through formation of an enol, and then it changes to another enantiomer. We can see here the dextrolactic acid is taken in 2 moles, and when it is heated, it is getting converted into the enol form, okay, which is D-enol, and this is unstable. So what happens? It then changes into another enantiomer, and that's how we get the mixture, that is the racemic mixture of lactic acid. Another example is of racemization of tartaric acid. Now, when this tartaric acid is heated for some time at 160 degrees, then it loses optical activity and it forms the racemic mixture and the meso acid. Now, this is because we can see here the dextro and the levo form of tartaric acid, and also the meso form, which is generally a racemic mixture. Now this is possible because tartaric acid has two asymmetric carbon atoms which may undergo inversion of hydrogen or hydroxy group about one of the chiral carbon. and because of that the meso acid is formed. And when it undergoes the inversion about both the chiral carbon, then it gives the racemic form of acid. So that is how we can carry out the racemization of the optical isomers. The third point which we can understand here is about the asymmetric synthesis, which is also called as chiral synthesis. So when a compound which contains a chiral carbon atom is synthesized by ordinary lab methods from a symmetric compound, then the product is a racemic mixture, which means that any compound that contains chiral carbon atom, right? It is synthesized by ordinary lab methods from a symmetric compound. The product is a racemic mixture. Always, whenever we want to convert any symmetric compound into the optically active form, then usually it is a racemic mixture. But when this synthesis we carry out in presence of suitable optically active agent, then we can successfully synthesize any one of the isomer, that is the dextro stereoisomer or the levo isomer. So for this we have to maintain suitable experimental conditions. So, from this we can easily understand the definition of chiral synthesis as a process in which a chiral compound is synthesized from a symmetric compound to form either a dextroisomer or a levoisomer is called as asymmetric synthesis or chiral synthesis. Here we have an example of this chiral synthesis. When we take an example of pyruvic acid and we carry out reduction in two different methods. In the first way, we carry out the reduction of pyruvic acid with nickel catalyst. So, if we see the product which is obtained, we get the dextrolactic acid as well as the levolactic acid. That means the product is a racemic mixture of lactic acid because we get both the isomers in half of amount. So, racemic mixture is obtained. But if we carry out the same reduction reaction, not in presence of nickel, but if we carry out the reduction by yeast, then if we see the product which is obtained, the lactic acid is actually the levoisomer only is obtained and dextroisomer of lactic acid is not obtained. So pyruvic acid upon reduction in presence of nickel catalyst gives the racemic mixture of lactic acid and in presence of yeast it gives levo form of lactic acid. Here are few of the important questions to practice which include like what is stereoisomerism, then what is the racemization, what is about the asymmetric synthesis, and moreover there are certain multiple choice questions which are also important from this topic. These are some of the references. Thank you.